you had to wait this long. You were supposed to be going through the software of Proteus, which you are going to use to complete practical 8, 9, and 10. The guys of electrical have gone through it on Tuesday. So we will try again tomorrow during your slot of electrical circuits, during your lecture of tomorrow, to see if you can go through the Proteus. We are going to discuss something called resonance in AC circuits, and maybe just to make it clear to those that might not be sure. The test is continuing. The test and the class tests are continuing on Saturday from 10 to 12. So what we're going to do is we would expect you to be at building 13. We will find venues when you are there. That's why we are not giving any venues, because last time when we went there, some lecturers decided to steal our venues and put their students and ride by force. So, yeah. So by 10 o'clock, we will arrive earlier, some of us, to see venues that are available, and then we will allocate you to venues that would be available, so that we don't have the disruption that we had last time when we were supposed to write. Now, what do we mean by resonance in AC circuits? You have learned quite a number of things that relates to your impedances, whether it's your inductive impedances, whether it's your capacitive impedances.
Sir,
yes?
The document you're talking about is not yet opened. I can see your file explorer right now.
You can't see resonance?
Yes.
Okay, I can see it. Okay, let me close it and reload it again.
Yes, perfect. I can see it. Thanks.
Thank you. So, maybe the question arises that what happens when you would have a series circuit that contains a resistor, an inductor, and a capacitor? We have seen that, obviously, if you are to calculate the impedance, if you are to analyze that circuit, if you are to try and see, what kind of a power factor you have in the system, inevitably you would need to understand which of the reactances is greater. If your inductive reactance, for instance, is greater than your capacitive reactance, then you would have a resultant inductive circuit. That would mean you are having a lagging power factor, you are having your current lagging, your voltage, and so on and so forth. All that information follows when you know the relationship between your inductive reactance and your capacitive reactance. Now, a question arises that what happens when the capacitive and the inductive reactances are equal? That is, what happens when XL and XC are equal? Remember, we have shown you that if, for an example, you are drawing the impedance diagram of an inductive circuit, you would have, obviously, your resistor is always positive, and your XL is also positive. Now, what that means is that it would be, for instance, in the first quadrant. You would have it in the first quadrant. Now, when you have, for an example, a resistor connected to a capacitive reactance, you have seen that the resistance, because it's always positive, and your XC, which is your capacitive reactance would be regarded as negative, and as a result, we will draw it in the negative imaginary plane, if you like, effectively drawing it in the fourth quadrant. Now, so what happens when this XL and XC are equal? So what happens is that XL and XC subtract each other. If XL, for an example, is 10 ohms and XC is 10 ohms, what would happen here is that omega L minus 1 over omega C becomes 0. It becomes 0. And when it becomes 0, we will say that your circuit is in resonance. A circuit is in resonance when both the capacitive and the inductive reactances are equal. So we'll also analyze the effect of these components under varying frequencies. So for instance, under what conditions would this be the case? So you know, for an example, that both XL and XC are functions of a frequency. XL and XC are also both of them dependent on the frequency F. So it means that regardless of the fact that L would have some certain value of henries, C would have some certain value of farads, we can work around a particular frequency, which when you substitute that frequency in these two equations, it gives us XL being equals to XC. And we will see under what circumstances that would be the case. So the point I've been trying to make is that if, for instance, we take XL as positive in that manner and XC as negative in that manner, what then is the relationship between XL and the frequency? We see that if you look at this equation, for an example, you can easily see that XL and the frequency is that of direct proportionality. So if you take 2 pi L as a constant, then you are actually seeing that XL and the frequency are directly proportional to each other. So this is a relationship of direct proportionality, while you can see that XC and 1 over 2 pi FC, this is a relationship of inverse proportionality. So meaning that when XC goes up, the frequency should be going down. When the frequency goes up, XC should be going down. So that is the inverse proportionality relationship that you'd expect to see there. So at a particular frequency FR, XL, so this FR is what we would call the resonant frequency, the resonance frequency. So we can do two things. We can find one frequency which equates XL and XC, or we can say we want to equate XL and XC at what frequency should that happen, right? Given their fixed values. So obviously the impedance will be purely resistive because XL is positive, XC is negative, and if they are equal, they will obviously subtract each other, yielding yielding the total impedance Z to simply be resistive. That is going to be the square root of R squared, which is simply going to be R. So below the resonance frequency, we can see here below the resonance frequency, so that is somewhere in this region, XL will be less than XC, and when that is the case, the circuit is capacitive. And when you are operating somewhere beyond the resonance frequency point, XL will be greater than XC, so that circuit will be inductive. Now, also, we know that we can be able to calculate what the angle phi is. What is the angle phi? In our case, angle phi is just the angle that shows the relationship between your voltage and your current in this instance. So what's the phase shift? What's the phase shift? And of course, the phase shift inevitably also would be a factor of at what frequency you are operating at, because, for instance, if angle phi is negative, it means that the circuit is capacitive. That's the current leading the voltage. If the angle phi is 0, it means XL is equals to XC. You simply have a resistive circuit, and the cosine of that would simply give you 1. You would be operating at a power factor of 1. And here, where phi is negative and the circuit is capacitive, you would be operating at a leading power factor. So you would be operating at a leading power factor. And of course, when you're operating beyond resonance, where XL is greater than XC, angle phi is positive. Angle phi being positive, you'd have the circuit being inductive, and the circuit being inductive means that you would be operating at a lagging power factor, where your current will be lagging your voltage. It's important to remember that when you have got a combination of XL and XC, you always try to find this angle phi using the resultant reactance as well as your resistor. That is, if you are using arctan. If you are using arc cosine, you'd have to use the resultant as well as your impedance, because that's what the relationship is. Now we want to be able to look at how do we find this particular frequency? How do we determine the frequency which would give us resonance? The frequency which would give us a situation whereby the XL is equals to XC. So that's what we do in order to find that frequency. We equate XL and XC. And we solve for FR. So you can see that how you'd want to do this is, if you cross multiply, you'd have something that looks like 4 pi squared FR squared L times C is equals to 1. If I cross multiply from this equation where I've equated XL and XC, I would have 4 pi squared FR squared L times C. And of course, that is equals to 1. Then what I do is I will divide throughout by 4 squared pi squared FR. I leave FR squared there. So I'll divide by 4 pi squared L times C throughout, so that I'm only left on the one side with FR squared. And then, of course, because I'm not looking for FR squared, I'm looking for FR, I take the square root of both sides, such that FR is going to be the square root of 1 is 1. The square root of 4 pi squared would be 2 pi, and the square root of just LC would be the square root of LC. So this is how you'd calculate your resonance frequency. That's how you calculate your resonant frequency. But what we know is that the radial frequency is always 2 pi f, the radial frequency, which is represented as omega. It's 2 pi f. So if I want to find what the radial frequency omega is at the resonant frequency, I'll simply say omega at resonance, it's equals to 2 pi f R, the frequency at resonance. So this is what you would have if you take this equation and you'll multiply by 2 pi, because this is f. To find omega r, you multiply this by 2 pi, you simply have 1 omega c. So what have you done here is you have, if I give you a particular inductor, a particular capacitor, and I say, you have got a circuit which has got this inductance and this capacitance. At what frequency can you achieve resonance? Then you would use this equation to calculate at what frequency you'd be able to achieve a resonance. Now, there's something that happens at resonance, which you would see. There's something that happens at resonance. And that something that happens at resonance is that The voltages across L and C can be very much greater than the applied voltages. Now, don't ask me why, I don't know. I have not found out why that is the case. Maybe that's something that I'll find out. But yes, what we are saying is that you would have a circuit that looks like this, where you have got an input voltage here of 100 volts, but you'd see 150 volts at this inductor. You see, so you find that the voltages at this components is much greater than the voltage that you put in the circuit. And I think that's quite an interesting thing to observe. But that only happens at resonance frequency. So there is what we refer to as the Q factor. The Q factor, it is the factor that we are going to use with the supply voltage. So your Q factor, what is the Q factor multiplied by the supply voltage, for instance, to see what is the voltage at your capacitor. So for an example, if the Q factor that you are going to calculate is 2, it means that the voltage across the capacitor is going to be 2 times the supply voltage. That's what it means. If it's 1.5 Q factor, then it means the voltage across your capacitor will be 1.5 times your voltage at your supply. So that's what you would have. So you would need to be able to calculate this Q factor as 1 over R, which is 1 over the resistance in your circuit, multiplied by the square root of the inductance of the capacitance. Right, so that's what you would have. So let's have a look at a quick example. A circuit having a resistance of 4 ohms and an inductance of 0.5 Henry and a variable capacitance in series is connected across a 100 volts 50 hertz supply. So now you have got a fixed frequency. So now if you have a fixed frequency, it means what we are going to calculate here, we are going to calculate here knowing in our case what the resonance frequency is. But we have got a variable capacitor. So we are going to have to know if we have got so much inductance and this frequency, what amount of capacitance do we need in order for us to reach a resonance or at resonance frequency. So of course we know the equation that relates the XL and XC at resonance to be 2 pi FRL equals to 1 over 2 pi FC. We are trying to find what the capacitance is, and in our case we are not calculating what the resonance frequency is because the resonance frequency is given, and in our case it's given as 50 hertz. So we would calculate what the capacitance is and would find it to be 20.3 times 10 to minus 6 farads, which is simply 20.3 microfarads. The voltages across the inductance and the capacitance. So at resonance, we calculate what the current is. Now, what we mean at resonance, we know at resonance that the inductance, or rather the inductive reactance, and XC, that is the capacitive reactance, are equal, with the inductive reactance being positive and the capacitive reactance being negative. So it means they will subtract each other, yielding a 0. At resonance, it means that the impedance, the total impedance of the circuit is just simply R. It's simply R from this equation. It's just R from this equation. Once this will go to 0, we would have the square root of R squared, which is R. So we are trying to find now what is the current that will flow at resonance. At resonance, we have got the voltage of 100 volts and the resistance of 4 ohms. It gives us a current of 25 amps. A current of 25 amps. So what is the potential difference across the inductance? We will multiply this current by XL. we'll multiply that current by XL. So what we have, we find that the voltage across the inductance is 3930 volts. The potential difference across the capacitor will be 3930 volts. Now, this makes sense. Why does it make sense? Because at resonance, the impedances are the same. XL and XC are the same. If this these reactances are the same, and the same current flows through them because they are connected in series, we expect to see the voltages to be the same. Right. So we want to then understand what then becomes the Q factor. We can use this equation to find the Q factor, where VC is equals to Q multiplied by V, or we can use this equation. This equation, the first equation on your left, is if you're calculating the Q factor, when you know the parameters, the resistance, the inductance, and the capacitance. This one on your right is I can then calculate the Q factor when I know the voltage across the capacitor and the total supply voltage. Because this Q factor will simply be the voltage across the capacitor divided by the total supply voltage. And we find the Q factor as 3930, the total supply voltage is 100. If you divide this by 100, you will get 39.3. You get the Q factor as 39.3. Right. Another example, you've got a coil of resistance 5 ohms and inductance of 1 millihenry being connected in series with a 0.2 microfarad capacitor. So in this instance, you are given all the parameters, the resistance, the inductance, and the capacitance. The circuit is connected to a 2 volts variable frequency supply. So the supply is 2 volts. The frequency is variable. So we are going to try to find at what frequency we can find the resonance. Calculate the frequency at which resonance occurs, the voltage across the coil and the capacitor at this frequency, and the Q factor of the circuit. This is essentially the same problem as what you have done, except that here now you need to calculate what we start with what resonance frequency is. Now this is the equation of resonance frequency. It's 1 over 2 pi, the square root of LC. All these parameters are given, and then you find that in this circuit we would be able to find resonance at 11.25 kilohertz. At 11.25 kilohertz. So we will not use, okay, you can do the other resonance. I didn't do the others, but you know already how you can calculate the resonance. Frequency, you know how you can calculate the voltages of the coil, the voltage of the capacitor, and also eventually you can be able to calculate what the Q factor is. Now, what happens when we have got a parallel circuit? Now, we are trying to then find what is the resonance at a parallel circuit. Now, we see that essentially at a parallel circuit, resonance will also occur not only when the impedances are equal, but when the inverse of the impedances are equal. When the impedances the inverse of your impedances are equal. For example, this is the inverse of your XC, and this is the inverse of your inductive reactance. When you equate that, you will find the resonant frequency. But essentially, the resonance frequency is the same. It's the same. So the equation you would use, which is this one, it's exactly the same frequency that you would use, whether your circuit is connected in parallel or is connected in in series. So if this is, for an example, your radial frequency, then you can, from this, it's easy to know that F subscript R is simply going to be 1 over 2 pi the square root of LC. So I think the point we're trying to make here really is that how you calculate your resonance frequency is not dependent on whether your circuit is connected in series or in parallel. You would calculate it the same way. The only difference, however, is when we were calculating our Q factor, when our circuit was connected in series, we had 1 over R, the square root of L over C. So that is essentially the inverse, if you like. So if you invert that 1 over R to R, and that L over C to simply C over L, you would find what the Q factor is when you are working with a parallel circuit, when you are working with a parallel circuit. So you can find that. Now, what impact would that have? The impact of the Q factor when you've got a parallel circuit would not be on the voltage, because the voltage will be the same. The voltage will be the same. What the impact would be on the current. So you can see, for an example, that the current IL and the current IC by extension would be the Q factor multiplied by the total current that is supplied by the circuit. So now, in this instance, you would be impacting on the current that flows in your inductor and the current that flows through your capacitor. And of course, that's how you would calculate your Q factor. That's it. That's all there is to it to a resonance in AC circuits. Now, the next time I speak to you about a lecture, I will be dealing with three-phase networks. I'll be dealing with three-phase AC networks. You know, it's something of an advanced electrical engineering, because it was actually, it's part of a syllabus that, for instance, students would do in S1, S4, yeah, S3, S4, somewhere there. So it's something that it's a little bit more involved as opposed to single phase. Now, you have done single phase, you are still going to write a test. I think immediately when you come back from recess, I'll make your test ready. Then once you do have written that test, then we will start with three-phase networks. Three-phase networks will be the last thing that we do in this course. It will be the last thing that we do in this course. I think we've done quite a lot. We have done circuits, DC circuits. We have done theories in DC circuits. We have done electromagnetism. We have done magnetic circuit, we have done inductance, we have done capacitance. Today we have done resonance in AC circuits. We have done AC circuit on its own, series and parallel and all of that, and impedances and power factor correction. So the last part of the course would be three-phase networks, and of course the power measurements using 2-watt-meter methods and so on and so forth. Which yeah, I prefer that we do it when you come back from your recess. Any questions?
Yes, sir.
Yes, Nakin. Can
you please share the slide right here on Teams?
Well, I can do that, but I'll also put them on Brightspace. Yeah. Any other question? Okay, if there's no any other question, we try again tomorrow to log on for the practicals, and maybe a little bit of explanation on how the practical is going to be done. You will be given a time to do practical 3, rather 8, 9, and 10, because all of them you're going to do them on simulations. All of them are quite similar to one another. So I give you time. Let's say I give you 3 weeks. I'll decide when the 3 weeks starts to do the simulations and then write the report. Do the simulations and write the reports. And then I will give you a date of submission. So on the date of submission, you will submit practical 8, 9, and 10. Now, on that date of submission, you will have completed your practicals. So you'd have done 1 to 7. The next time when you submit, you are bringing 8, 9, and 10. So we will be done with practicals. We'll be out of practicals. I'm also planning to give you an assignment before you go to recess, so that you do the assignment during recess. When you come back, you will come back for a test and a class test, that is test 3 and class test 3, and then you'll be submitting an assignment. I'm not sure if you'll also be submitting practical 8, 9, and 10. I will try to make the dates different so that, but I can also make them the same, more especially for this class. I can try and put them on the same date so that it reduces the logistics, you know. You know that on this day I've submitted everything, I'm fine. But I'll communicate the dates for the submissions. Usue, let's hear. That's correct. That's correct. So it increases according to the factor, the Q factor. So if you would have calculated the Q factor to be 1.5, it means the currents in your inductor and your capacitor would be 1.5 times the total current of the circuit, yes. Thank you. Okay, thank you, good people. We'll speak again some other time. Thank you.